Okay, and here is chapter 3. This is the first part of chapter 3. So in chapter 3, we threw out a lot of interesting things about the history, but you don't have to know the history for any of the learning objectives for this chapter. So this is just interesting stuff. You do need to know a few things, and this is also where I started adding the learning objectives so that you could look back within a section and see the learning objectives. So you need to understand these terms. So you need to be able to understand that the amount in a certain time, the amount of waves in a certain time is the frequency. And the frequency we use this like little number to represent. And you can see that on the left there's a whole lot more waves. That's high frequency, and on the right is low frequency. There's just the one part of a wave in it. You need to understand frequency. The units for frequency is s to the minus 1, which is the same thing as 1 per second or as a hertz. Those are all the same thing, and they're interchangeable. You also need to know that this distance right here, we use this guy, and he's called a wavelength. And notice that on this side, the wavelength, where it's high frequency, the wavelength is shorter right here than, say, over on this side of the chart. Right here, you can see that this is longer. And you know that this is the high energy side of the chart, so lots of frequency and short wavelength. But all those things together indicate high energy, and then low energy is where you have not very many frequencies, or not many waves, low frequency. And you've got a really long wavelength. And then the last thing is amplitude. Amplitude is the half height. So if you wanted to see something that was higher amplitude, that would be higher amplitude, and it would also be going lower. So that's amplitude. For light, that would be a dim object might look like this, and then like a really bright object would have a higher amplitude. You need to understand those terms. You need to know for sure that we use this symbol for wavelength and we use this symbol for frequency. There's definitely some things that you need to know about the equations. So I have this list of equations, but the main ones that you need to know, this is going to be given. And I put this one on here like this, but the one that's given is going to be E equals h nu. So I gave this one because I wanted you to know that you can plug this equation in over here. You can plug that in and you can get to this other equation. So you have to be able to use the two equations together. You also have to make sure you're doing them in the right units. So there are some example problems that we worked. And I just realized that I opened the one that doesn't have all the work on it. All right, sorry. This one has all the work on it. Okay. And so you can always have the straightforward version of the equation where you are given information. So if you're given frequency, that's this guy right here. If you're given frequency, it is not hard at all to get to wavelength. If you're given this, and if this is a constant, we just have to rearrange the equation to get to wavelength. So what we did was we divided both sides by our frequency, and then we canceled out that frequency. That's how we ended up with just a wavelength equaling our C over frequency. Once you get that, you put in things the way that the stated. So I rounded the light, and that's fine. It might make things easier. The speed of light will be given, so C is given. And rounded up to 3, that's fine also. And then you need to know that your frequency goes in at the bottom, that the number right here is the frequency, and that it goes in that bottom space for this equation for when we're solving it. And that should give you your answer. And then here's another example of E equals hc over lambda if you're using this version. Now this version won't be given. You're going to have to be able to get to it. But h times c, that's a constant. So this is a constant and this is a constant. The lambda is what you were given in the problem because they want you to use this wavelength from above. That's just the wavelength from above. And you put these all in the calculator and you're going to get a number. And you'll notice I was trying to show how the units work. So a meter cancels with a meter, and then your seconds cancels with the seconds, the -1 seconds, the seconds on the bottom right here. And that leaves you with a joule, which is the unit you want everything to be in. You could have also worked this problem one other way. You could have used this version, E equals h times the frequency, if you wanted to go up to this problem and use the frequency that was given. So if you're going to use the frequency, you can do it that way. And so you have your 6.626 times 10 to the -34th joule seconds times 4.28 times 10 to the 14th 1 over seconds. Notice that your seconds cancel like that. And you can put those in the calculator. And when you put them in, you should also get that same number. And I know that feels like the easier way to work it. So in this case, this equation is what's given on the test. That would be the easier one to work it with. But you need to be able to also work with this version of the equation where everything is all in there. Because there are sometimes when you'll be given energy and you'll be asked to solve for wavelength. And you're going to have to get to the bottom number. And this is kind of proving that you can get to that equation. And then these are just more problems. This one right here is worked out exactly. So the only difference in these problems and the one above is that the units aren't quite right. So you'll notice right here, there was a first step before you could plug anything into the equation where you had to take that unit and then you had to convert it into another unit, which is a hertz. Or seconds minus, you had to convert it into something else. Now we're back to that familiar seconds minus, and we can plug it into this equation right here. That's where he went in. We couldn't immediately put this in because this wasn't in the right units. It had to be in a hertz or a 1 over a second to be in the right unit. So that's more common. I definitely think that you need to make sure that you're good at this and you can recognize if you're in the right units to use these equations. There's going to be other equations in chemistry and other chapters coming up. Same issues. So you want to get used to it now. And here, right, in this case, this one, you also wanted to find the energy. If we have E equals hc over lambda, you know your H is right here. That's a given constant, and this is given. Again, these will be given. They are on a formula sheet. You do not have to have this memorized. But you need to have your energy. This is what we calculated over here, and it's going right there. You need to know what your energy is. The way we got from this equation right here to this equation was we multiplied both sides by lambda. And in doing that, this lambda cancels with this lambda. And then we divided both sides by E to get the E on the bottom. So first, we multiply both sides by lambda. Which made this lambda cancel. And we were left with lambda times E equals hc. And then we divided both sides by E just to get that lambda by itself. You're going to do that on your own. I'm going to take those off. And make sure that you can do them on your own. You can get between those equations. And that's just like straight up math. And here's just another example problem for you to work to make sure that you're really, really good at calculating these things. This section right here, this Bohr's line spectrum, what you need to understand from it is like more of a conceptual idea. And I'm trying to find exactly how we phrase the principle on here. Ah, here it is. Okay. You need to understand that electrons are found at specific energy levels called shells and subshells. So, for example, this electron right here, he's on the first shell, the first energy level. He's right there. And they can be on different energy levels, but they're going to start at the bottom, and then you're going to feel your way outwards. You need to know, I'm trying to find where this one is. You need to know that as you go further and further out that between these little areas, that this is going to take less energy because they're closer together for that electron to jump. But like here to here, this is going to take a lot more energy for that electron to jump. So you need to know that. So the further are you out, like 3 to 4, that's a lot less energy than like 1 to 4. You need to know that we have something over here, and it's called this line spectrum. And you need to understand that this line spectrum, and that these little lines that are in this line spectrum, they actually mean something. And they correlate to the electrons in an atom being jumped up in energy level. And you don't necessarily have to know which energy level, but you have to know that it means that they're jumped up in energy level. And then when they fall down back to that place that they were in, they give off energy. That energy is what we see. There's something you need to know about energy too. We didn't make a big deal about in this lesson, but energy, when it's being lost or like given away, that is negative. It's going to be a negative energy, and we call that an emission. But energy that is gained or put in, so this would be like when the light hits the electron, it's going to be gaining energy. That's going to be positive, and that's absorption. When you go back up to the Bohr model that we had that picture of, you need to know that it has some strengths, and you also need to know that it has some weaknesses. So some of the strengths is this idea of the electron being quantized, the idea of energy levels. One other thing that's incorrect is that the electrons don't do a planetary orbit, so that's incorrect about that model. You need to understand that this idea of quantized energy states are very, very important. This idea that you can be here or here, but you can't be in both places. And you can't be at the area in between. You're either in one place or in the other place. That's also very important. And you need to know that when we get to the section where we're talking about the quantum mechanical picture, what changed from Bohr, because again, he theorized the energy levels being quantized, so that's great, and that they're energy levels and that they can only be in certain energy levels. But the idea of that planetary orbit is not correct. So instead of orbits, we have orbitals, and they describe the region that you find the electron in. So that's different than just an orbit. The Bohr model also, one of the weaknesses is that the Bohr model looks flat, and this is all three-dimensional stuff. And these are, if you weren't sure, these are the characteristics of the quantum mechanical model of the atom. And the last little bit from this part that you want to make sure that you're really clear on is that the idea of the Heisenberg uncertainty principle, sorry, it's right here. This is directly related to this idea of being an orbital, because Heisenberg is saying, like, you're not looking at a specific position for the electron because you can't find that position as well as, like, the speed, because it's constantly moving. You can't find them at the same time without affecting them. So that idea came to the idea of, oh, it's just in a region. So Heisenberg, he came to that idea of, oh, the concept of the electrons being in a region. It came from Heisenberg's uncertainty principle. All right, I think that's it for the first half of chapter 3.